rates of change, and related rates. The derivative as a rate of change. Given two quantities represented by variables x and y, with y equals f of x, the secant line slope, f of x1 minus f of x0 divided by x1 minus x0, is the average rate of change in y with respect to x over the interval x0 to x1. The derivative f prime of x0 is the instantaneous rate of change in y with respect to x at x0. So the instantaneous rate of change is the limit of average rates of change as interval width approaches 0. Examples of rates of change and their units. We'll look at a few examples here and discuss a dependent variable, an independent variable, and the rate of change in the dependent variable with respect to the independent variable. For instance, we might be concerned with a variable such as water temperature, in which the dependent variable we might denote by capital T, and it might be measured in degrees Celsius. Now, an independent variable of interest could be depth, x, in feet, and we might expect the graph of T versus x to look something like this. In other words, we would expect the temperature to decrease as the depth increases. The rate of change in temperature with respect to depth would be the derivative of T with respect to x with units of Celsius degrees per foot. In another situation, we might be interested in the area inside a circle. The dependent variable would be the area capital A, and we may be measuring that in square centimeters. An independent variable we could use is the radius r in centimeters. We actually know what the graph of this function looks like because a is pi r squared. The graph of a is a parabola opening upward. The rate of change in the area with respect to the radius is the derivative of a with respect to r, and its units would be square centimeters per centimeter, which simplifies to simply centimeters. In fact, a is pi r squared, and dA dr is 2 pi r by the power rule. Notice that dA dr is precisely the circumference of the circle, and that's consistent with the fact that the derivative of a with respect to r has units of length. Now let's think about automobile gas mileage. Let's let capital M denote mileage in miles per gallon. That's our dependent variable. We may be interested in the relationship between mileage and cruising speed S in miles per hour. M might have a graph that looks something like this. Notice we get better mileage as speed increases up to a point, and beyond that point, mileage starts to decrease. So the rate of change here is the derivative of M with respect to S, and its units would be miles per gallon per mile per hour, which simplifies to hours per gallon. The idea of rate of change is perhaps most familiar when the quantity of interest is a function of time. For example, a ball is dropped from the top of a building. Let h of t be its height in meters after t seconds. Then the derivative h prime of t is the velocity of the ball in units of meters per second. Here's a typical graph. Here the height of the building is 100 meters, and it takes about 4.5 seconds for the ball to hit the ground. Now let's look at an animation that shows how this graph is formed. Here we have the ball initially at height 100. The triangle will move along the t-axis, marking time in the animation. So now let's drop the ball. Secant line slope here is average velocity. Now, for instance, the secant line extending from the initial point on the graph to the final point has slope delta h over delta t, in other words, change in height over change in time. The ball is dropped 100 feet, and the difference in the times is roughly 4.5, or in other words, there's a time interval here of about 4.5 seconds. And so the average rate of change turns out to be about negative 22 meters per second. It's negative because up is the positive direction for height and the ball is falling. Now, tangent line slope corresponds to instantaneous velocity. At the instant when the ball is dropped, it has zero velocity. But as it falls, its speed increases, that is, its negative velocity gets larger until it hits the ground. So our main point here is that for an object moving along a vertical path, velocity is the rate of change in height per unit time. Suppose that a pond is stocked with a small number of fish, and let P of t be the number of fish in the pond t months later. The graph of P versus T might look something like this. Notice that the population increases fairly slowly while the population is small, and then levels off as the population approaches some larger value that corresponds to the greatest number of fish that the pond can sustain. The average rate of change over the 36-month period graphed here is the slope of the secant line in the figure. We estimate that the population has increased by about 270 fish over the 36-month period, so the average rate of change is about 270 divided by 36, or 7.5 fish per month. The derivative P prime of t is the rate of change in the number of fish at time t. That is, P prime of t is the population's net growth rate at time t. Here's the graph of P prime that corresponds to the function P graphed above. Now let's notice that there are actually two times at which the tangent line to the graph of P is parallel to the secant line. In other words, there are two times at which the instantaneous rate of change is exactly the same as the average rate over the entire interval. Those times are simply the times when P prime has the value of 7.5. Now again, as we noted before, P increases slowly at first. In other words, the slope of the tangent line is small at first. The rate of increase gradually increases up to a point and then decreases thereafter. We can also see this in the graph of P prime. Now notice that there's an interesting point on the graph of P. It's the point where the slope is at a maximum. In other words, where the derivative is at a maximum. Notice that at that point, the shape of the graph of P changes. This kind of point is called an inflection point. We'll discuss inflection points in more detail later. The diagram on the left shows a simple electrical circuit consisting of a resistor, a switch, a current meter, and a capacitor. A capacitor essentially consists of two metal plates that are separated by an insulator, and it's capable of holding an electrical charge. We'll assume that our capacitor is initially charged, and when we close the switch, it will discharge through the resistor, and the current meter will indicate the flow of current here. So let's close the switch and watch the graph of the charge on the right. It turns out that current is actually the rate of change in the charge on the capacitor. Using the letter I for current, I of t is equal to Q prime of t, where Q is charge. Related rates. Example, let V be the volume of a sphere with radius r. v equals 4/3 pi r cubed, and suppose that r and v are changing with time with rates dv dt and dr dt. So imagine that the sphere maintains its shape while changing size in some fashion. We can relate these rates by differentiating each side of the volume formula with respect to t. This type of differentiation is sometimes called implicit differentiation because we're differentiating with respect to a variable that doesn't appear explicitly in the equation. The key is the chain rule. The derivative of v with respect to t will equal the derivative of v with respect to r times the derivative of r with respect to t. So we take the derivative with respect to r of 4/3 pi r cubed and multiply by dr dt. The power rule tells us that the derivative of 4/3 pi r cubed is 4 pi r squared, so we have 4 pi r squared times dr dt. A way of thinking about what we've got here is the fact that if either rate is now known, we can find the other one at any given value of r. Here's another example that's similar. Let V be the volume of a cylinder with radius r and height h. Our formula there is V equals pi r squared h. And suppose that r, h, and v are all changing with time with rates dv dt, dr dt, and dh dt. So imagine that the cylinder is maintaining its shape while its dimensions r and h are changing, causing the volume to also change. The relationship among these rates is found by differentiating with respect to t as follows. Here both the product rule and the chain rule are key. The derivative of v with respect to t is the derivative with respect to t of pi r squared h. Remember, we're thinking of r and h as functions of t. We need to use the product rule here. We'll take the derivative with respect to t of pi r squared and multiply by h and add pi r squared times the derivative of h with respect to t. Now, the derivative of pi r squared with respect to r is 2 pi r. Using the chain rule, we multiply that by dr dt. So now we have dv dt equal to 2 pi r h dr dt plus pi r squared dh dt. If two of these rates are known, then we can find the other at any given r and h. Here's an example of a classical related rates problem. A rotating spotlight beacon is located 1 mile from the closest point P on a straight shoreline. The spotlight makes 30 full rotations per hour. How fast does the light move past a point on the shoreline that is 1 mile from P? Now let's begin by drawing ourselves a diagram. Let's suppose this is the shoreline, and suppose this is the spotlight beacon. The point P is here on the shore, and there's a 1 mile distance between the beacon and P. Now at any given time, the spotlight might be directed towards some point along the shore, and we may as well assume that the rotation is clockwise so that the direction of movement of the spotlight is up the shore. Now let's let y be the distance from P up to that point where the spotlight is shining. Then, the rate at which that point is moving is the derivative of y with respect to t. Now we need to relate y to some other variable here. And since we know how many rotations the spotlight makes per hour, let's define theta to be the angle shown in the figure. Then, we know that the rate of change in theta with respect to t is equal to 30 rotations per hour times 2 pi radians per rotation. Or in other words, 60 pi radians per hour. Now, since we want to know how fast the light moves past this point on the shoreline that's 1 mile from P, let's think about what's happening when that distance is 1 mile. Here we have a right triangle with two sides of length 1 mile, and so the value of theta then is pi over 4. So what we want to find is dy dt at the instant when theta is equal to pi over 4. Now we need to find a relationship between our variables y and theta. This is very simple because the tangent of theta is y divided by 1, so y is just tangent theta. Now we differentiate each side of that equation with respect to t. dy dt equals dy d theta times d theta dt by the chain rule, and since the derivative of the tangent function is secant squared, dy d theta is secant squared theta, and so dy dt is secant squared theta times d theta dt. And so dy dt when theta is pi over 4 equals secant squared of pi over 4 times d theta dt, which is 60 pi. Since cosine of pi over 4 is root 2 over 2, secant squared of pi over 4 is 1 over root 2 over 2 squared. Root 2 over 2 squared is 1/2, so 1 over that is 2, and so we get 2 times 60 pi, or 120 pi miles per hour, which is approximately 377 miles per hour. Here's one more example of a related rates problem. A water tank has the shape of a cone with height 2 meters and radius 2/3 of a meter. If water is pumped into the tank at a rate of 3 cubic meters per hour, how fast is the water level rising at the instant when the tank begins to overflow? So our tank looks something like this. Its height is 2 meters and its radius is 2/3 of a meter. Now at any given time, it contains a certain amount of water. So let y equal the depth at time t. In other words, the distance from the vertex of the cone up to the surface of the water. Since we know that water is pumped into the tank at a rate of 3 cubic meters per hour, we know that the derivative of the volume with respect to t is a constant 3 cubic meters per hour. Now the speed at which the water level is rising is just the rate of change of y with respect to t. So we want to find dy dt at the instant when y equals 2, which is when the tank begins to overflow. Now we know that volume for a cone is 1/3 of pi r squared y, and the radius r and the depth y are related. To see that relationship, let's draw a triangle that represents half of the vertical cross-section. Here we have a height of 2 and radius of 2/3. And we have another sort of underwater triangle with sides labeled y and r as in the figure. Now by similar triangles, we can say that r divided by y is the same as 2/3 divided by 2. Or in other words, r is always 1/3 of y. So we use that in our formula and obtain v equals pi over 3 times y over 3 squared times y, or pi over 27 times y cubed. Now we take the derivative of both sides of that equation with respect to t. The derivative of v with respect to t is its derivative with respect to y, which is pi over 9y squared by the power rule, times dy dt by the chain rule. Substituting dv dt equals 3 into the left-hand side, we now have 3 equals pi over 9y squared times dy dt, and so at any time while the tank is being filled, the derivative of y with respect to t is 27 divided by pi y squared. And so at the instant when y is equal to 2, we have 27 over 4 pi meters per hour, which is approximately 2.15 meters per hour, which after we multiply by 1,000 millimeters per meter and divide by 3,600 seconds per hour becomes about 0.06 millimeters per second.